I'm sharing my screen. Okay. So I think my screen is visible. Okay. So here today we'll start with this gate level modeling and data flow modeling in the Verilog. Okay. First we'll see the gate level modeling, and after that we'll come with the data flow modeling. So if you see the gate level modeling, um, one second. If you see the gate level modeling. Okay. One second. Yeah. So gate level modeling. Mm, okay. Okay. Gate level modeling. Gate level modeling, you have logic gate primitives are there. Okay, logic gate primitives. We'll use logic gate primitives. Okay, so logic gate primitives like supported gates. So that means gate level primitives we are using like and or okay, and next XOR, NAND, NAND, and next NOR. Okay, NOR, XNOR, XNOR, and buffer. Okay, buffer, and next inverter. These are the gate level primitives. Okay, so gate level primitives we'll use. Okay, so like if you see, so the syntax. So how the syntax will be there? So the syntax for this gate level modeling will be like this syntax. So you have uh, let us take supported gates. It will be suppose AND gate is there. AND gate is nothing but gate level primitive. Okay. So syntax I can write. Okay. So here this is gate level primitive. Gate level primitive followed by instance name. Gate instance name. Instance name, and followed by output 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 comma input 1, input 2, like that. Okay, input 2, like that. Okay, so this is the basic syntax for gate level modeling. So let us take suppose and. Okay, and so for AND gate, what will be there? That means gate level primitive. Gate level primitive is AND out, out, in one, into, up to so on, like this. Okay, in N, in N. Okay, and for R, what will be there for R? So the gate level primitive is R. Okay, same thing. Out, in one, into, so on, in N. Okay, for OR gate. Okay, for OR gate OR. Okay, and next for the XOR gate. If you see XOR gate, XOR gate. Okay, for XOR gate, gate level primitive is XOR. Okay, same thing. Out, in one, into, so on, in N. Okay, and similarly for NAND gate also. Okay, for NAND gate also, gate level primitive is NAND out. Okay, out, in one, into, and in. Okay, and next XNOR also. NAND NOR. Okay, NAND NOR. For NOR also same thing. Okay, for XNOR also. XNOR also. Okay, XNOR. So it will be like this. XNOR. So same thing. Okay, this is same thing. and next buffer. Okay, so buffer, in buffer you have like buffer. There is a tri-state buffer, buffer one. Okay, so buffer one means here there is a tri-state buffer. So that this is a buffer, there is an enable signal. Okay, so a and output y. Okay, there is an enable signal, that is enable. Okay, so when enable equal to 0, this is active high enable. Okay, so active high enable, when enable equal to 0, so what you will get, that means enable equal to 0, you are getting y equal to what, z, it will be in high impedance state. Okay, when enable equal to 1 only, you are getting y equal to a. Okay, y equal to a. Okay, so you can use that means buff if buffer for buff if that is a buff if 0. Okay, this is for buff if 0, buff if 0, and you have output comma input. Okay, output comma input. So what is the output hereby? Input is a. Okay, you can write. And buff if 1, so buff if 1, so buff if this is buff if 1, a buff if 0. So buff if 0 means what? This is a buffer. This is a buffer, and you are giving through the bubble. Okay, when equal to 0, then you are getting the y equal to a, and when e equal to 1, you are getting high impedance state. Okay. So buff if 0, you have output output comma input. Okay, output comma input. Okay, like this you will get. Okay, and not if so not also. For inverter also, not if 1. Okay, output and input, not if. So you have tri-state inverter, in tri-state one more enable pin will be there. So this enable pin is acting as a control line. Okay, similarly not if 0. Okay, output y comma. Okay, so this is a gate level modeling, and this is not synthesizable. Suppose example, if you see basic example like for 2 cross 1 mux. Okay, if I want to write the program for 2 cross 1 mux. Okay, so how to write? Just I'll write the program for what, 2 cross 1 mux. Okay, so I'll write the program for 2 cross 1 mux. Okay. Okay, so here if you see, yeah, so I'm writing the program for 2 cross 1 mux. Example. So if I write the program for 2 cross 1 mux. Okay, so this is a 2 cross 1 mux. How many inputs are there? 2 cross 1 mux. How many inputs are there? Two inputs are there. So A, B. Okay, two inputs are there. And how many outputs are there? Only one output is there. How many selection lines? One selection line. Okay. So here, so I'm writing the program for this. So that means what is the Shannon's equation? Y equal to S bar A plus S B. Okay, this is the Shannon's equation. Okay. So from this, I can draw this one. So here I will draw the logic for this. So this is what this is one AND gate. Okay, one AND gate, and here selection line I am giving through the inverter. Selection line I am giving through the inverter. Okay, so this is A. Okay, selection line it is coming through the inverter. Okay, selection line. Okay, and next this is B. This is B, and selection line is directly coming, and it is given to one more AND gate, and here I need to consider this is nothing but select underscore n. Okay, select underscore n, and this is let us take the wire y1 and wire y2, and these outputs are connected to what? These outputs are connected to an OR gate, and this is 1. Okay, so for this I need to write the Verilog code. Okay, for 2 cross 1 marks. Okay, how to write? So see here. So here I'm writing the program for with this one for Verilog code. So first I need to start with the module. Okay, module. What is my module name? Module mux marks. So what is the output? Output is means you need to initialize the port list, or otherwise you can initialize the ports within the bracket also. Okay. So port list declaration. What are the inputs? So input A. Okay. Input A, comma B, comma selection line. Okay. And next output Y, output Y. Okay. I declared. Okay. And next I need to initialize wire. Okay. Wire. What are the wires? Y1, Y2. Okay. Select underscore N. These are the wires. Okay. So this one is nothing but not. And let us consider this is a instance name A1 and A2. Okay. And this is not is A1. Okay, let us take not is A1, and this and is A2 and A3 and A4. Okay, so here I can write this one not of what is the instance name, that means A1. What are the inputs? So output is what, select underscore n comma select. Okay, and next what I can write, and so gate level primitive and gate A2, and what is the output? Y1 A select underscore n. Okay, these are the input for this AND gate. Okay, this is the AND gate, and this is a NOT gate, and this is the AND gate, and this is the OR gate. Okay, and next and A2 A3, this is the instance name. For this, what is the output? Y2 comma B. This is B. Y2 comma B comma select. Okay, and and over. Next R A4 A4. What are the input for this one? Output is Y. Inputs are Y1 Y2. Okay, Y1 Y2 and 8 module. 8 module. Okay, so like this we can write the program for gate level modeling. So we can write the program for all the gate level modeling for all the combination circuits, like half adder, full adder, half subtractor, full subtractor, mux, demux. Okay, encoder, decoder. Okay, comparator, 1 bit comparator, 2 bit comparator. Like this we can write the program. Okay, so I'll show some programs related to this gate level modeling. Okay, so you see this programs related to gate level modeling. I'm opening this Xilinx Vivado. So I'll open some programs. Mm, Verilog programs. All gates. This one is all gates GLM. Okay, this program is related to all gates GLM. Okay, I wrote the all gates by using GLM. Just to see. Okay, how I wrote means all gates, AND gate, OR gate, NOT gate. Okay, all these programs I wrote with this GLM. Okay, this way. Yeah, this is the all gates GLM. So here I wrote the program for all gates GLM. One second. Sources. Okay. Yeah. So here I wrote the program for all gates GLM. Here if you see the program, uh, yeah. So here if you see the program, yeah. So module all gates GLM input I am using a vector 1 down to 0 in out y and y or y and y nor y xr y x nor y not y buff. Okay. So how I am initializing and output, what is output y and what are the inputs in 0 in 1. Okay. Or also y or in 0 in 1 and y and in 0 in 1 nor y nor in 0 in 1. Okay. XR, YXR in 0 in 1, YX nor in 0 in 1, not Y not in 0 in 1, buffer, Y buffer in 0 in 1. Okay, this is single buffer. So for this I need to, so this is GLM. So you can see the circuit also. If you elaborate this design, okay, if you elaborate this design, you can see the circuit, how the circuit will look like. Okay, so see here. So this is the gate level modeling. So you have like the two inputs are there in 0 and in 1, and it is coming through the buffer. Okay, this is AND gate only. Okay, AND gate, Y AND, and next you have AND followed by AND. This inverter is NAND, and here you are getting NOT, and directly you are getting buffer. And next OR, okay, OR, this is OR gate followed by this inverter NOR and XOR, okay, XOR, you are getting XOR followed by inverter, you are getting XNOR, okay. So this is basically the schematic for this all gates, okay. Run the behavioral simulation. I want to run the simulation. So if you run the simulation, you will get the simulation waveform. So you see, so just fit to page, expand this fit to page. So for these are the, so for two inputs, okay, two inputs 0 0, what will be the output? Okay, for AND gate OR gate, for AND gate output is 0, for NOR gate output is 1, and AND gate is also output 1. Okay, for 0 1, okay, how many possible combinations? 4 possible combinations I will 0 1. Okay, what is the output of AND gate and OR gate, all those things. And for 1 0, okay, one second, fit to page. For 1 0, what is the output? Okay, for 1 1, what is the output? Okay, like this, you can see the simulation part. Okay. Simulation part. So I'm closing this. Next, you can open. This is all gates. Mm, GLM, logic gates. Mm. This is half adder using NAND gate. Okay, half adder using NAND. This I'm closing. This is half adder using GL. Okay, gate level model. Next I'm opening and I want to show how to design this half adder using this NAND gate. Okay, NAND gates. First you need to design the XOR gate by using NAND gate, and from that you will get that one. Okay. So you need to know about the diagram, how to design the half adder by using NAND gate. So here, so I initialized so half module half underscore adder underscore GLM, input A, input B, output is sum and carry. So here, if you see, so whatever the input variables are there, that I need to initialize y w1, w2, w3. Okay. So NAND of so this is N1. So this is basic NAND gate. Okay. So W1 A comma NAND gate, and this is carry of W1 W2. Okay. This is carry. Okay. And for XOR operation, you need to do this one. Okay. You need to do this one. NAND of W1 A comma B, NAND of W2 A comma W1, and NAND of W3 B comma W1, and NAND of sum of W2 comma W3. Okay. So if you see, that means 1 second. So here, if you see, I think you know how to design half adder using NAND gate. Okay, half adder using NAND gates. Okay, NAND gates. So if you go for images, so we require how many NAND gates? So this is the half adder using NAND gate. How many NAND gates are required? So total you want four NAND gates. So here this is nothing but XOR gate. Okay, that initial variables I declared as W1 and W2, and here this is char. Okay, so you need to take the diagram and you need to initialize the internal variables and you need to write the functions. Okay, so if you elaborate the function, I want to elaborate the design. Just you need to elaborate the design. Just elaborate the design. How to design the NAND gate using this gate level modeling. See, this is the NAND gate. Okay, NAND gate. This is the elaborated schematic of half adder by using only NAND gates. Okay, simulation also you can see. So run the behavioral simulation. Here you are getting that. Okay, you need to write the test bench, but test bench I didn't wrote. Okay, okay. This is about gate level modeling, and next we will see the data flow modeling. Okay, I hope this gate level modeling is clear. Okay, I am going to data flow modeling. Okay, what is this data flow modeling? Okay, so data flow modeling. So in data flow modeling, we need to use the continuous assignment statement. That is 1 second. Yeah. So in data flow modeling, you need to use a continuous assignment statement. Okay. Yeah. So data flow modeling. So what is this data flow modeling? Okay. Data flow modeling means we need to use a continuous assignment statement. Okay. Continuous assignment statement. Assign. Okay. Assignment statement. Okay, so here this assignment occurs whenever the value on the right hand side changes. Okay, this whatever this continuous assignment, this assignment occurs. Okay, assignment occurs whenever whenever there is whenever there is so whenever the value on the right hand side changes. Okay, so the value on the right hand side changes. Okay, the value on RHS RHS changes. Okay, RHS changes. Okay, so we can assign the values to the nets only. Okay, so we can assign values to nets. Values to nets. Okay, we can assign the values to nets. So this will execute parallelly. This will execute parallelly. Okay. For RTL coding, we are using this data flow modeling. Okay, this can be synthesizable. That means we can convert this one into hardware. Okay, and this is continuously active, and this is continuously active, continuously continuously active. Okay, so this is syntax. What is the syntax for this continuous assignment? Syntax for this is assign, assign. Okay, assignment statement, assignment statement. Okay, assignment statement. So here let us take wire uh, x y z or assign I initialize the xyz as a wire So x equal to what? X equal to a this and c. Okay. Assign assign y equal to a or b. Okay. And assign z equal to b. These are the logical operators. This I will tell you. Don't worry. This is b xr of c. Okay. B xr of c. Okay. Or suppose wire I'm considering x, y, z. These are the variables. Okay. Reg a comma b comma c. Okay. So here assign x equal to what? A and b. Okay. X equal to a and b. Here no error. Okay. No error will get. Okay. No error. But Okay. Assign a equal to a or b. Here you will get error. Why? Because you'll get error. Why? Because the LHS should not be a range data type. Okay, LHS should not be a range data. Similarly, assign. Let us take b equal to b xrc. Okay, so here also you get error. Okay, so like this, these are the assign statement. Okay, so I will try to write the Verilog code for this full adder circuit using data flow modeling. Okay, full adder circuit by using data flow modeling. Okay, how to write the Verilog code. Okay, see here. Suppose full adder you already know. So what is the full adder? So that means if you see the full adder circuit. Okay. So here, if you draw the diagram for the full adder, you got like so full adder circuit. If you see, so basically you already studied no full adder circuit. Sum equal to what? A XR B XR C and carry out equal to AB plus BC plus AC. Okay. Data flow modeling means you need to initialize with the expression. That is nothing but data flow modeling. So if you see the diagram, so this is one XOR gate. This is one XOR gate. Okay, here AB, and these output is given to one more XOR gate. One more XOR gate, and this is C out. So this is A XOR B XOR C out. Okay, C out, and carry equal to what? AB, and so AB, BC, and AC. Okay, AB, and one more expression is there. No, AB plus A XR B into CN. That is also carry out. Okay, like this also you can give. Okay, A XR B. So here this is A XR B, and this is CN. This is nothing but CN. Okay, A XR B into this CN connected with an AND gate. These both are connected with an OR gate. Okay, so here how I can write the Verilog code for this full adder circuit. So here I need to initialize the full adder. Okay, so Verilog code will start with the module module full adder underscore data flow Okay, what are the inputs I can initialize? Okay, input A comma B comma C in, and output S comma C out. So I can declare two styles are there now. I can declare within this. Okay, and I am using assign statement. Assign. By default, you are not declaring any data type, means it will declare like a wire data type. Okay, so it will declare that wire data. A sum equal to what? A XR. This is logical operator. A XR B XR Cn. Okay, A XR B XR Cn. Assign C out. Okay, C out equal to what? A and B, or A and C. Okay, A and C, or A and C in, and B and C in, and end module. Okay, so like this I can write the program. This data flow modeling I will show you. Okay, One second. So here you see the data flow modeling, how I wrote DFM. I think this is there or not. Just I will check. For all gates, I wrote with the DFM data flow modeling. Okay. Okay. DFM also we can write, but it's not there. One second. DFM need to write. Okay. Mm, I can show the pro. I can show you the program. One second. So DFM. See here. Uh, mm, One second. All gates. RTL. Large icons. DFM. Okay. So this is the program for DFM. Okay. So if you see the program for DFM, module all gates underscore DFM. So input 1 is to 0. I'm using vectors concept. Input 1 is to 0. Okay. Output Y and output Y or Y and Y and Y nor Y XOR Y XNOR Y not Y buffer. Okay. And is the assignment statement. Okay. So assign Y and equal to what? In 0. This is the logic bit level AND operator. Okay. Bit level AND operator. In 0 and of in 1. Assign Y or equal to in 0 or of in 1. Assign Y and equal to not of in 0 and of bit level and of in 1. Assign Y not equal to not of in 0 or of in 1. Okay. Assign Y XOR equal to in 0. This is XOR operation. Okay. And this is XOR. Not of this XOR and not of this in 0. And buffer means what? Y buffer equal to in 0. Okay. So this is the Verilog code. This is the Verilog code. So next test bench means so if you see the test bench, how to write the test bench here if you see, I wrote the test bench also. Okay, for using DFM module, data flow modeling. So here in the test bench, select this font size. Okay, module all gates DFM underscore TB. I need to initialize 1 is to 0 using the vectors. Okay, two inputs will be there for the gate. For the using whatever the inputs are there, I need to initialize with range, and whatever the outputs are there, I need to initialize with the wire. And next, I need to instantiate. Okay, so instantiate how I designed connection by name. Okay, connection by name. In the industry, we are using connection by name only. So that means this is the design name. What is my design name? All underscore gates underscore DFM. Design under test. This is the instance name. Dot y and dot y or dot y and. So whatever the variables outside the bracket are nothing but design inputs. Okay. What are the variables inside the bracket? Those are nothing but test bench inputs. Okay. And next, what I given, I initialize the I as integer, initial begin, dollar monitor. This is a system task. If there any change in the inputs, there is a change in the, it will display the outputs. Okay, this is a system task. I'm using for loop for I equal to 0, I less than 4, I equal to I plus 1, begin, in equal to I, okay, and hash 20, and dollar finish. Okay, this is test bench. Okay, so this one, just copying in this guidance Vivado. Okay, I will open this. I'll show you the show this. Okay, 1 second. Mm, yeah. So see here we will have programs. All gates GLM, all gate GFN. Okay, here I will write. I'll open this. So see here it's opening. This is nothing but GVim. Okay, basically GVim is powerful editor. We can use this one for Quasta sim. Okay, so here design source, go to design source, add, create the design source, create the file. Okay, that same file, it should be same file. What is my file? You press I, it will be editor. All gates underscore DFM. So copy this and paste this. Okay, finish. Okay, all gates. Okay, yes. Okay, so all gate DFM is created. Okay, so just double click this. So double click this, and next here just delete this. So whatever that design file is there, no, just copy this file and paste in this. Okay, just save this. Okay, save this. Okay, after saving, you need to create the test bench file. Okay, for creating the test bench file, you need to go to simulation file, add this, add or create simulation sources, create the file. So test bench file. What is the test bench file? I. Okay, this is my test bench file. One second. Yes, this is my test bench file. Just copy this. Okay, and just paste this. Okay, already exists. Okay, one second. Simulation source. Okay. Mm, simulation source. Create. DFM. Get 100 for DFM. TB1 available. Okay, TB1. Create. Finish. Okay, TB1. Okay, so TB1 that will be created. Here also I will change. Okay, this is DFM TB1. Okay, save this and just to copy this file and save in this simulation file. And so save this. Okay, save. So it is created. Okay, so it is created. If you want to see the elaborated design, so open the elaborated design. It will show the elaborated design. It will show the elaborated design. Same design will get. Okay, for weight load modeling and data flow modeling, same design. Whatever I explained, same design will get. Okay. Suppose if you want to simulate, so here what I wrote this. Uh, I wrote the for loop, no integer I and that for loop I wrote. So that means it will check for four possible combinations. Okay. So it will check for four possible combinations. Fit to page. See here. So these are the two inputs. Okay. Initially, let us take inputs are 0, 0. Okay. So 0, 0 means what? And or inputs are 0 only, and or are 1 only. Okay. See here. And or are 1. Okay. And next XOR is 0 only, and XNOR is 1. Okay, not is 1 and buffer is 1. Okay, similarly you can see for 1 0 1 case. Okay, 0 1 case, and is 0 and or is 1. Okay, NAND is 1 and NOR is 0 we get. Okay, and XOR you are getting 1 only. Why? Because or detected. Okay, similarly 1 0. So 1 0 means AND is 0, OR is 1, NAND is 1 and NOR is 0, and XOR is 1 and XNOR is 0. Okay, like that. If it is 1 1, AND is 1, OR is 1, and AND is 0, and NOR is 0, and XOR is 0, and XNOR is 1. Similarly, NOT is 0, and the buffer is 0. Okay, this is behavioral model. Okay, so like this, so you can see for DFM, data flow modeling. So like that, you can write for the behavioral modeling also. Okay, so this is about DFM. Mm, some DFM codes for GLM I wrote. Mm, this is about data flow modeling. Okay, mm, gate level modeling. Mm, data flow modeling. So combination circuits, if you see the combination circuits. This is a simple combinational logic I wrote by using data flow modeling. Okay, this is a basic combinational logic, Mux's means combinational logic I wrote. Okay, so this is about gate level modeling and data flow modeling. Okay,